Uh, this thesis is based on primarily the first paper here and uh, additionally the other two papers. I will just move on from that. Okay. So, embedding language, like by doing next token prediction, we end up with language models that conduct some sort of an intermediate hidden stage to predict the next token. Now, the fun part is that this intermediate hidden stage is a multi-dimensional vector space that has that is continuous and has nice properties. So essentially, we end up with okay, language is discrete. Uh, we have a bunch of sentences. These are now points on a vector space that is full, and we can move around in this vector space. So that leads us to the interpretability question, rather, is does this space and the relationship in these spaces, do they correspond to the relationship between sentences or meanings and concepts? And additionally, we ask, can we define functions on these spaces that correspond to meaningful semantic differences, right? And that's a theme that's gonna keep coming up. So for this, I will first begin with linear representation hypothesis. It's largely unproven, but it's used as the intuition backbone for a lot of interpretability research because it empirically seems to have checked out multiple times. So the idea is that these language models have ended up disentangling semantically relevant attributes linearly. And if that is correct, then what can we do with that? And to that extent, to that end, there's like a bunch of probing studies which essentially ask questions about uh, what has a language model learned, and then there are other studies about erasure and steering, things that I'll more talk about, which is once you know that a language model encodes a concept, how easy and clean is it for us to make changes along the lines of that concept? And that's going to be, so essentially, I had to mention this for the philosophical underpinning, right? So steering, I mean, this is one illustrative diagram of what we're talking about, but essentially the idea is that, okay, we have some sort of a guess about how these embeddings work, and we want to verify them in terms of the changes we can make to the output of the language model. And being able to make these changes reliably implies that our understanding of these embedding spaces is sound. And that is what my work largely cares about. How do these embedding spaces behave, and what can we assume about them? Uh, at any point, please interrupt me or stop me, by the way. Uh, So this is just an intuition image, but like I just wanted to give you an intuition of how, like, where the, I don't know, the inspiration comes from. And it's just that when you have images and when you are in the continuous space, you have these nice visualizable examples where you can change one attribute about the image and that changes the style or whatever else. In sentences, that is not clear to us immediately, but essentially the intuition here is that once the sentences are embedded, you get something that looks like this in that latent space, if that makes sense. So that's the intuition of all the different functions that I'll be talking about today, right? Okay, research gap. So existing work was largely empirical and practical in the sense that people knew that if you wanted to change how a generation is going to like end up, they would take some sort of a classification data set, let's say toxicity, and they would do a forward pass on both the classes. They would take the average on both ends. They would do the mean difference. And they would add this every time, I don't know, they want to change where the direction is headed. And that worked relatively well, right? First thing is, it was not well justified theoretically. Why should this work? Why should not anything else work? For instance, let's say I trained a probe to, like a linear probe, to classify that concept. Why can't I add this linear probe directly and why doesn't that change things? And just for context, a probe is just a classifier trained to be positive when toxic and negative when non-toxic. So why can't I add or subtract this vector instead of this mu naught minus mu one vector? That's the motivation here, right? So it's a heuristic, no theoretical framework. That's a problem that we recognize. So this leads me to like a list of contributions, right? Uh, First thing we do is we provide a theoretical justification for steering values. And in so doing, we like essentially relate this to related work in erasure, which I will describe later, and related work in optimal transport, which I'll briefly mention. Second, once we have this theoretical framework, we use it to define stronger steering functions, and like by adding more constraints, which I'll describe properly later, and that leads us to better results, which we verify empirically. That is the third contribution. We show results in debiasing, domain adaptation, and output control specifically for toxicity, right? So I'll just move on. Okay, so previous work has had talked about this concept of concept erasure, which is that I have an attribute that I want protected, and let's say that is gender. And the idea is that after I am done with my operations on the embeddings of the language model, any classifier that was after this will not be able to use the gender attribute. And B, it's like, I mean, there are statistical guarantees that I'll go into, but yeah. Now, this was primarily used for debiasing and was based on this definition of the concept of guardedness. This is guardedness. So we are talking about affine guardedness, which is this WX plus B. And we are saying that a function f is guarding with respect to a particular concept C. And let's say, and okay, from now on, I will be assuming that C is a binary attribute. So let's say C could be small c and small c dash, right? Two classes. So the idea is, the definition is simply that the best eta classifier, affine classifier, should be the worst possible thing you can get. That's like the intuition here. So it's saying that I get the best eta and I get G such that it is the worst possible value, essentially. I think that's the translation of this expression. Now, because eta also includes constant predictors, so we call this particular expression trivial loss. That is, if the best possible classifier should be the one that has a favorite class, and it's just giving you 0, 0, 0, 0, 0 all over, and that's the trivial loss. So essentially, this expression says that the function that will do the guarding will lead us to a situation where the best possible classifier is a constant predictor. I hope that makes sense.
So f is your guarding function?
Yes, f is the guarding function.
And g is?
So g is like all possible affine functions. So the f is the function that gives us the supremum over g. Supremum by maximizing the loss.
So h is your LLM features.
Yes.
F is your guarding feature.
Yeah.
G is affine versions of f.
Yeah, all possible affine parameterizations of f.
And eta is?
The classifier. So eta is parameterized by
theta.
Theta. Yeah.
Theta is shared.
Yeah, essentially. So it's the unbound variable, so to speak. So inside we're just saying that it's the best possible classifier every time. And now we're saying that the worst.
So when you say best possible classifier, you say that on this set of features, guarded features, if I train a linear probe.
Yeah.
Then the classifier is that after linear probe, the classifier you're talking about.
Yes, yes.
To classify what, now I can't figure out what the gender is. Right?
Exactly. So, I mean, here you're training the probe. Here I'm saying that you actually trained a very bad probe. So this is equivalent to saying that I changed my embedding such that the best possible classifier is the one that picks a favorite class and sticks to it, a constant predictor, also known as trivial loss.
Constant or random? Let's say it can't predict gender, means it.
Yeah, I mean, okay, that is randomly choosing. So it turns out to be equal to a constant predictor. Proof that was established, but I'm not covering it again.
But it will depend on what case you are, so, okay,
Yeah.
depending on what sort of, okay, basically it's a constant entropy classifier.
Yeah.
Sort of, you mean?
Yeah.
Okay. Or highest entropy.
Exactly, highest. In this case, like highest cross entropy, yeah, basically, yeah. So we are basically trying to ensure that the best possible classifier is the highest entropy classifier. That's, I think, the succinct way of putting it, right? So, yeah, I mean, I have already gone through this, but the last part, existing work by Rose et al. Showed that the previous, this definition implies that the best function, which I've written here as G, is the one that will equate the means of the two classes. So if I somehow ensure that the means of the two classes are the same, then I won't be able to draw a good classifier. It'll suck. Yeah. Now, this is incomplete for steering because all I did as of now is remove a concept. So if I'm, let's say, trying to control for sentiment or toxicity or whatever, I'm trying to control the output, this did not give me any guarantee on where my final output lands up. And that is not good. So that's like, but I went into erasure because it allows us a very nice jumping point to how we are going to define steering next. So because of how erasure works, we are going to say that, okay, what if the right steering function is the one that takes the two conditional distributions and makes one look like the other in some way? That I'm going to keep vague for now, black boxed it, but that's the constraint we're going to talk about later. But in some vague notion of similarity, these two distributions should line up to the right distribution, to the desired distribution. So at the end of it, the relationship with erasure for our work is that we are removing the difference between the two classes, but we care about where they land up. That's like the differentiation point. So so the first thing I talk about is, okay, what if I just wanted to map the means of the two distributions, the first moment, and I'm going to search over all possible piecewise affine functions that are only applied to, let's say, after checking whether you are in the right place or not, and I'm going to minimize the mean square error, and that is the notion of minimality. I could have chosen other things, that's fair, but we just choose mean square error because that's the default. So the point is, like, essentially we want to equate the means with the smallest change possible. That's all this says. This solves two steering vectors. So essentially, we have now provided a theoretical justification for why steering vectors make sense. Because once you solve this constraint optimization problem, you end up with mu c dash minus mu c, because W star turns out to be I. So, yeah.
C is the class, the topic you're interested in.
Yeah.
That C is the corresponding, so content of H corresponding to what you want to negate, or let's say.
No, so capital C is the thing that I'm controlling.
H subscript C.
Yeah. So the small c is
No, the
subject.
second. Yeah.
Sorry.
Yeah, here
Yeah.
what is C?
Yeah. So C is like the right class. So it's the wrong class, my bad. Yeah. So it's C dash is the right class. So essentially I'm saying that whenever it's C dash, we don't apply anything. And whenever it's the wrong class, we try to equate it to like essentially this. Now, once we do this for all the samples, this is the best way to get this.
So your main solution. So you're saying H. So you're doing a mean square between H and all possible affine, like whatever.
Yeah, exactly.
Affine D, whatever the set of affine functions.
Yeah.
Of H, you want to equate that subject to that SHC should be equal to HC dash.
Yeah.
So is this, so HC would mean some subpart of H, I believe,
Yeah.
which you want to preserve.
Yeah.
So my understanding would be.
No, we are preserving C dash.
So go to last slide. Go to last slide. Read the last before this.
Yeah.
Read this. So we want to do smallest change possible to is preserve semantics unrelated to Z.
Yeah.
So now come back to next slide. Isn't it like you want to preserve what is unreliable? So okay, or
let me just so there are two things, right? One is the capital C control attribute. Let's say that for this equation. So capital C is the control attribute, and it takes values from, let's say, C and C dash.
There's only one C in this equation. Really, the subscript is the same C you have used.
C dash.
C and C dash. So
Yeah,
don't
C
say
and C
capital
dash.
is confusing. Okay, C and C dash.
C and C dash. Yeah. Now we're saying that for H given C is equal to C and H given C is equal to C dash. So let's say if I always, let's say by some oracle, I could ensure that I will always get toxic sentences, for instance. Then that would yield the hidden state distribution.
So HC is H given C is equals to C.
Yeah.
Right? So that's fine.
Yeah.
Okay. So their mean is what you're equating.
Yeah, basically. So it's just saying that the smallest way to, for the whole population, the smallest way to equate the means. And
the rest you want to preserve because you want to keep the rest the same.
Exactly.
Okay.
Now the point is that now this essentially
so that's your optimization function.
Yeah.
Now you're saying how to solve that.
Yeah, this is the solution to that. I'm going to go into the proof of this like immediately next.
Okay. So can you describe this again? The solution.
Yeah. So it's just because W star ends up being I, so it just ends up being for all things that are C and just normal for all things that are C dash, which is what I had earlier introduced when I said it is popular to do mu naught minus mu one. So this is the solution that leads to that, essentially. So this is an explanation for why that works in a way. Was that?
Yeah, I'm just seeing 2 minutes I'll take.
Yeah.
See the W star is actual an identity or
it ends up being the identity. Like the solution
or you hope it to be the identity.
It's the solution which I'm gonna go into.
Okay.
Yeah.
Take.
Just to okay, I mean I can open since like it's affine S, I can just open up that and I can just say that it's H minus WH.
Forget about the free format. What in practice you do? In practice, do you end up with? In practice, when you solve whatever empirically, when you will be doing the experiment to sort of support this, what happens in that case?
So I will take this solution. This I can get from my data set. I will take this exact formula. I will turn
and
that.
And there you use W as identity?
Yeah.
Okay.
That W is identity.
Okay. Well, go ahead.
Yeah. So, I mean, but like we solve this closed form, and the solution to that is, I mean, I will just only show the verification here, but you can see that, like, I will make the Lagrangian, I will add the constraints. When you do a derivative with respect to W, is equal to 0, you end up with that, where the sigma C tilde is just the expectation over HH transpose.
I only saw one W in the last equation.
Sorry?
I only saw one W in the last equation.
There is only one W, yeah.
So this is the W of your LLM?
No, W is the thing that we are
the thing you're saying.
That will turn out to be identity.
Yeah. Okay, so that's what you're solving for, right?
Yeah.
So you can't assume this is identity at this point.
No, I'm telling you right now that
it come out to be
that it came out to be identity.
That's what the confusion was. So you're solving for W, you're hoping it to be identity.
No, I mean, because we have already done the work, we already know that it's identity. Okay. So
at this point it was confusing because to me sort of I felt why it became identity. Suddenly, okay, you go ahead.
Oh, right. So yeah, that I'm coming to that later, essentially. Yeah. So okay. Yeah.
So now optimize this with respect to W.
Yeah. Sigma C is expectation over HH transpose, which is like cross covariance plus mu mu T.
Go back to the last equation. Yeah, so you say H is this, and now it's a piecewise function you have. So your H star H. So only at SH you will have the W equation.
Yeah.
So you equate. Okay, all right, good. Next one. Fine. Yeah, I'm just trusting the solution is fine right now. Yeah, not able to mentally do it, but it's okay.
I mean,
all right.
like
So SH it will come. Yeah, it's okay. Which should be right. Of course, you have a paper on this.
Yeah.
But I'm just okay. All right. Go ahead. Yeah, go ahead.
Yeah. So I mean, like here, I mean, if like I only kept the verification bits of the proof here, but essentially, well, once we set all these 3 to zeros for the Lagrangian, we get 3 equations, 3 variables. If you put W as identity here, and if you put B as oh, I mean, B is already, I mean, essentially it's like mu C dash minus W mu C.
Right.
It works out. Like all of the equations will work out. There's no like violation essentially. Okay. That's the check. Okay. So I mean, this solves out. But now the point is that we put one constraint here, which was the first moment of distribution, and the original casting I had given was that we are going to make the distributions look alike. So the immediate next thing I'm going to do is that, okay, match the second moment as well. And that leads us to trace this. And that's, I mean, I'm checkpointing that right now. This is the solution we have.
So basically, till here, you're just saying that if the means match,
Yeah.
so the second moment also match.
Okay,
then,
now I'm saying that. I hadn't said that yet. Yeah.
But you're saying that these two match.
Yeah.
If I'm able to somehow match them, because
with the smallest change possible.
Will not be obvious. Theoretically, it's fine. But if I can match, then okay, for that, whatever I want to, let's say, erase or so on, I can sort of
control
that.
Yeah. I'm just saying that, let's say I am trying to control the generation. I'm just saying that I have a desirable distribution in mind. I can get that desirable distribution by, I mean, okay, I'll go into how I get that.
The mean and second moment, first moment and second moment.
No, I'm not going, I mean, not going there yet. I'm just saying that, okay, let's say there exists a desirable distribution, but the language model doesn't always adhere to that desirable distribution. So now I'm saying that when it doesn't adhere to that, I'm going to match mean and second moment, and that with the smallest change possible, and in the experiments we will hope that works.
I'm going a bit ahead. So in practice, what do? You just distribute with this distribution also, that distribution also. So and then you learn this.
Yeah. So in practical, what happens is that, okay, you give me a classification data set, sentences, labels. I run my LM through all the sentences. For all labels 0, I take them to one side. All labels 1, I take them to the other side. These are things that I can calculate immediately, cross covariance, blah, 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 and W star, I multiply that, I get W star, I get V star similarly.
And now I have to do the transformation while you are doing the operation.
Exactly. And now I just do this transformation as the thing goes.
So basically, crux is you just matching the first two moments.
Yeah, first two moments with the smallest thing possible. Yeah, that's the crux. Yeah. Similar proof, except I borrowed some things from the previous proof directly. Essentially, it's like, okay, I mean, setting B to 0 will lead to that. Here you will notice that there are no B or lambda terms because we had that previously. I just put that in here. If you want me to go back to that, I'll just show you.
No, that's fine.
Yeah.
This is fine.
Yeah. And the Z term is for the new constraint. And the subtle thing this gives us is that the final transformation must be symmetric.
So is the lambda same for both? Like, so you had Lagrange multiplier there also, here also.
I mean,
they're different set, no?
I mean, they're just like, it's just another variable. It just so happens that
it will be a different variable, but you use the same one here, no? It will be a different Lagrange multiplier for first moment and separate one, but you end up using lambda just for the.
No. I mean, so it's like, since we are carrying the same constraint forward, right? These are two constraints. The first constraint was there previously also. I just use lambda for the first constraint.
Lambda you
Yeah.
again use for this first constraint.
Yeah,
Second constraint
exactly.
you will use some other variable.
Which is z, capital Z.
Okay.
Yeah. And because like lambda doesn't show up anywhere else and z doesn't show up anywhere else, we borrow a lot of things from the previous equation. So after that, it's like slightly standard. I do my partial derivative with respect to capital W, set that to 0. After like a whole bunch of different things, we get Z plus Z transpose is equal to I minus W inverse. It's important because it tells us that W has to be a symmetric solution. And that eliminates a lot of solutions to this equation, which is W sigma C, W transpose, sigma C dash. So, I mean, just to recap, this was the solution to that. If you put it in all of the equations, it will verify. That's just it. Now, this is the intuition part. What is the difference between all these? It's like the 2D illustration here basically shows that in the first case, which was the first constraint, you didn't match the shape. And in the second case, you match the shape and the thing, right? That's like the deal here. So, I mean, obviously, there's no a priori reason to believe why matching the shape would help. So we test that empirically, essentially. Just like a more theoretical grounding to this stuff, there's another thing that this is related to optimal transport. In the sense that when we define, like just to recap on what OT is, we have the Earth mover's distance, and it is defined as essentially finding the joint distribution that preserves two marginal distributions such that this expectation is the smallest possible, right? And the mapping that leads, so this equates to the mapping that leads to one distribution resembling the other. For arbitrary complex distributions, you need arbitrarily complicated models. But it just so happens that if you somehow knew that HC and HC dash were Gaussians, then the solution that we provided for the two constraint is the optimal transport solution for those two distributions. And that's just like a fun detour. But yeah.
This is approved by someone else.
So this Norton's that optimal transport is solved for that. It just happens it's the same transformation. So that's the relationship. Yeah. So I will now go into the experiments. Before that, I will just describe a bias metric. And it just says that, okay, assuming you have a multi-class classification problem denoted here by Y, and you have a binary controller attribute here denoted here by C, then for a given instantiation of Y, the probabilities should be as, like the difference in probability should be as small as possible. So given an unrelated attribute, my classifier should not have a wildly different behavior. That's largely it for a given class of profession. For all of the classes, you just like essentially do a mean square and average. So that's the metric. These are the results for debiasing. The data set here is called bias in bios, which is that you have a bunch of descriptions of what people do, and you have labels for what they actually do, which is multi-class, and you have labels for what gender they belong to. And the idea here is that we will make everything male or make everything female, assuming binary gender. And we will then like check how different the classifier is. So like the left table is just that the accuracy should not go down a lot, and the TPR gap should go down a lot. And that largely works out. The baseline here, okay, the second baseline that I've written as least here is the Belrose et al. Result for erasure that we had earlier mentioned. So, like trying to do debiasing with steering works better with direct debiasing. It works better than direct debiasing methods, right? This is more interesting to me personally. It's just that the question is, what is the percentage of k nearest neighbors that share the protected attribute? So I took all of these vectors out, and I plot them in some space, and the point is that I should not be able to guess gender by their neighbors. And so the lower this is, the better this is. And the original models are there. And when you do mean matching, it's a little better, but not quite there. When you do mean and covariance matching, it's gone. So that's that. This is domain adaptation, kind of. So it's like we have a data set which has essentially for two axes. One is like whether it's in the African American English dialect, and the other is what sentiment it belongs to. And what this experiment is doing is that we are introducing a spurious correlation of the African American dialect with a sentiment by partitioning the data such that that correlation exists. And the percentage on the x-axis represents that. So the idea here is that if it's very spuriously correlated, then the TPR gap will be very high. So while here the difference between mean and covariance matching is not a lot, it's very far from the original model. These are for control generation. Everything that we have compared against either requires like full parameter fine tuning or requires full gradient calculation and multiple samples for each token step. And we like this way of steering is competitive against that. Just to go in and just to describe the table to you. So typically, so there's a data set called real toxicity prompts, which is completely different from the data set from which the statistics were obtained. So there's no like leak or whatever. So there's real toxicity prompts, which is just prompts where people know that models behave weird. So we take out 25 generations for each of them. We apply the different things to them, and like we take the worst one for each prompt, and that's this metric here. And this metric there is just the fluency, which is like whether those sentences make sense. Trigger warning, I will just show you some samples if you are interested. So large is like unintervened and intervened. That's prompt self-evident. I will move on after a few seconds. Yeah. So now, like I come to towards the end of my talk, which is we talk about larger implications of what we have discovered. And the primary philosophical thing here is just that there's a lot of value in looking at continuous distributions of language embeddings, because I mean, like sentences are weird and like very chunky, but as soon as you're in the embedding space, you get a lot of flexibility. The second point is why I mentioned our relationship to optimal transport, because maybe a lot of wisdom from the image domain and other continuous modalities can be applied in LM interpretability research, because that's the domain in which language models operate. Third one, which unsatisfies some people, is just that linear assumptions are very powerful. I mean, they're not the end of everything, but they are powerful. And finally, it just gives you a cheap way to do these things. Like, for instance, the interventions that we have talked about have no backward calculation at all. It's just like one forward pass, calculate everything zero form, and just apply it as a linear layer. So that's nice in terms of like, quick ways of controlling language models. Future work. First point is something I'm still slightly interested in, and like I think a question you only had earlier like put in my head, which was like the effect prompts have on the final representation space of the language models, and is that something we can model in a nice clean way? Probably not, but we should try. And the other thing is how are these, like in terms of expressivity, how are steering functions related to prompts? The second thing is, okay, I mean, yeah, I already talked about that. Third, multi-class control attributes. Things actually get meaningfully different when you have multi-class control attributes, even if you are talking about affine functions. So that's important. That's something we don't deal with. Fourth, multimodal models. I mean, this is a theme that I've been harping on about from the start of this talk, which is just that uh, like we are trying to treat these representations spaces as how like people deal with like images and such. So now how does that change when you have actually multimodal models in the same space that are putting all the different modalities? What can you do from here and there, right? uh Acknowledgements. That's it. I'm open to questions. Thank you for listening to the talk.